next speaker is David Clark, Director of National Security Education Center, Los Alamos.
All right, I brought a few slides. Now, normally I like to walk around and work the audience, but I know I have to stand here, right? So this is a little unusual for me. But I was a member of Malcolm's group. I joined in 1982, and I want to talk a little bit about what it was like being a student at that time. And I knew that lots of people would come here today to talk about all the wonderful things about Malcolm as an individual. And I wanted to tell a little short story, so I guess I drive here from now. Sorry, I got it. Okay. A little short story. It's not even my thesis work, but it was kind of captured the excitement of being in Malcolm's group at the time. Now, I love this photo. This was taken when Malcolm was inducted in the National Academy, and the title, Malcolm Chisholm in His Element. And look at the case of molecules. That's the first thing. When I joined his group, and there's a bunch of them across the back here, there are about 100 more that seem to be missing. And Malcolm loved these molecules. He had a metal box. Do you guys remember that? He had a metal box, and he would put these molecules in, and he would ship them to wherever he was going to give his talk, and he would hand them out and pass them around. I mean, he was so enthusiastic about it. And so these molecules meant a lot to him. And for the students who made them, they also meant a lot. I'm going to say one little story about Malcolm that talks about his character and his caring as a person. And I'm going to tell you about a little bit of science. This may have happened to many students. I got a phone call one day. It's Malcolm. Now, Malcolm used to call me a lot. But on this day, he called and he said, what do you need from me? I said, what are you talking about? I don't need anything. He says, oh, come on. Everybody calls me. They want a letter of recommendation. They're trying to get an award. They want something. You never ask me for anything. So what do you need? And I said, Malcolm, when I need something from you, I will ask. But it says so much about Malcolm, the person who cared deeply and genuinely about every one of his students, to actually reach out and say, what do you need from me? It wasn't what we could do for him. What do you need from me? I will always remember that about Malcolm. It says so much about who he was as a person. Okay, so I joined the group about 1982. You can see we were both younger then in this picture. And I wanted to study electronic structure. I said, Malcolm, I really want to study electronic structure. And he said, I can't teach you electronic structure. I said, you have to learn how to do chemical synthesis. That's what my group is all about. If you learn how to do chemical synthesis, then I will send you somewhere where you could learn electronic structure. Now, at the time, I thought this was the standard blow-off. I would disappear, I would go do synthesis, and that would be the end of it. And I'm going to come back to tell you about Malcolm, the man who kept his word. So it always starts with synthesis. I just want to illustrate a little bit here. There's solid-state synthesis. Early in the sort of Princeton days, it was all about molybdenum. At the time I joined the group, tungsten was becoming more interesting. How the heck do you get into this low-valent tungsten chemistry? There's some of you in the group smiling because you were involved in some of this work. This tube furnace reaction here where we'd put tungsten hexachloride in with red phosphorus. We'd heat it up, we'd distill out phosphorus trichloride, you'd seal that off, heat it a little higher, you'd get the oxo impurities to sublime out. This was a pain in the ass, frankly. But when you were done, you had this lovely ampule of a few hundred grams of really beautiful tungsten tetrachloride that would go right into THF. Actually, I do have the tool, so I don't know if you can see that. Yeah, this molecule right there, actually originally reported by Dick Schrock. Our group got involved, and I mean, this was a team effort, right? The whole group got involved to find out what it really was, and it was this so-called green salt, which became known in some circles as the Chisholm green salt. And there's a whole story that I can tell you at the bar later about this if you're interested. And actually, there should be 3 bonds. There's a Mac PC conversion here. It was 3 bonds. I'm looking at a clip. It was 3 bonds when I emailed it. I'm just saying. So, right there. Yeah, it's true. Right? So then, with 6 equivalents of lithium dimethylamide. Now, as an American, you had to learn how to say that, dimethylamide. That was the British way, right? It wasn't dimethylamide. And you can make this molecule here. That is a triple bond. It's not a half bond, Cliff, okay? Right there. This beautiful staggered ethane-like geometry that became known as, in our circles anyway, as the Chisholm-type triple bond, sigma 2 pi 4. Malcolm called this the cheerleader molecule, and that was because he had his moments, right? And so there was restricted rotation around the metal-nitrogen bond, and you can study that by NMR, and then there was restricted rotation around the metal-metal bond. So he would say, it whirls and it twirls, and from those of you at IU will remember he said that IU had yelled, "Go Big Red." Right? And that was Malcolm's sense of humor. Now, it had this sigma 2 pi 4 triple bond, and it was like acetylene. And Malcolm was absolutely fascinated with the analogy between the multiple bonds of organic chemistry and the multiple bonds of inorganic chemistry. And he set out, I would say, for 15 years or so, to systematize the chemistry of the metal-metal triple bond. And he showed that it undergoes oxidative addition, reductive elimination, ligand substitution, cycloadditions, cluster-forming reactions. This was an exciting time to be in the Chisholm group, I'll tell you. It was really something. Again, it continues with synthesis. Chlorotrimethylsilane, you guys can see it. There's a real Mac PC thing going on here. I may have to pull out my memory stick because Malcolm would be really unhappy to see a double bond there. So you make this 1,2-dichloro, there it is, 1,2-dichloro triple bond, and you could alkylate that with alkyl lithium to make the 1,2-dialkyl. This is a lot of work, a lot of synthetic work to get up to the point here on the bottom where Bill Vandersloot at the time put an acid anhydride in, and it made this fascinating molecule here with this ditungsten tetracarboxylate with 2 axial alkyls. Now, I'm not going to go in. There's a really cool, lot of interesting stuff going on. I don't want to bore you all with it, but I want to tell you, actually, there's more than one way to make it. That was always true in Malcolm's group. Bob Tatz remembers making the 1,2 of the alkoxide. You could then add acid to that. Or even in a really spectacular reaction, those who've ever made ditungsten hexaneopentyl, that's a pretty active molecule. And we were shocked that you could actually add an acid to that without it catching on fire and giving alkane and the dialkyl. So many ways to make these things. Now the big question was, this is really a bad slide because these are all triple bonds. But the big question was, what was the electronic configuration? So on the left we had acetylene and the Chisholm-type triple bond, sigma 2 pi 4. And at the time there were several other examples in the group. If you had 6 carboxylates, you could have this weak axial interaction here. Or if you had a carbamate, you could have equatorial alkyls. And they were all the sigma 2 pi 4 electronic configuration. And then this is the quadruple bond. You can clearly see the 4 bonds there. And then we had this thing. And the question was, what was it? And so this was a time when Malcolm got the whole group together. This was Bill Vandersloot's project. But suddenly we had the whole group fascinated and working together as a team. And that teamwork was one of the lessons that I learned from Malcolm. So Dave Hoffman was in the group. He was a Roll Hoffman student. He did some extended Huckel calculations. I'm watching the clock. Whoever's watching me, don't worry. And those calculations were consistent with pi 4 delta 2. But it was an extended Huckel calculation, and nobody would believe it in those days. And the thing was, if this sigma orbital dropped down low enough, it could actually be pi 4 sigma 2. And what we couldn't understand at the time was that the metal-metal bond in this D3-D3 dimer was actually shorter than the quadruple bond in ditungsten tetracarboxylate. It was 2.18 and some error, and 2.22. How could that be? So we couldn't understand how could this D3-D3 dimer have such a short triple bond. So we needed some higher level of theory. And this is Malcolm Chisholm coming out as a man of his word. And he came to me and he says, okay, apparently by this time I'd proven that I could do synthesis. I'm told that was true. You can decide. But Malcolm said, all right, so you want to do theory. I'll give you a couple choices. There's this young upstart at Ohio State by the name of Bruce Burston, who was on his tenure track in those days. He said, I think it will be good for you to go work with Bruce. So I spent the summer in 1984, I believe, here with Bruce. In those days, you did all your theoretical work at night, because that's the only time you could get computer time. Anyway, so we did that. So I came here, worked with Bruce. To make a long story short, we were able to use a higher level of theory. In those days, it was X-alpha scattered wave. It was the John Slater technique, kind of the precursor to DFT. And I've simplified the picture for you here, but this is the quadruple bond, sigma pi delta. And when you interacted two alkyls, you were left with this pi 4 delta 2 electronic configuration. But those orbitals that one would ascribe to being metal ligand bonding, metal carbon bonding, were also extremely, I don't know if you can see this very well, this is how we did orbitals in those days, by the way. It took all night to plot these things, right? Whereas now you push a button and you get a 3D thing. But this was the metal-metal sigma bond. It's also metal-carbon sigma bonding and metal-oxygen sigma bonding. And so it was really, as we published this paper, it was a D3-D3 dimer with a quadruple bond. And that was Bruce's title, because Bruce was always into getting provocative titles. We then went back to prove with electrochemistry, this was Bill Vandersloot, that in fact electrochemically that first electron to come out was indeed a delta type electron. And then we went to Dennis Lichtenberger. Ed Kober was there at the time, and we did photoelectron spectra to show that in fact you were really ionizing a delta and pi electrons, and here was the quadruple bond. There's sigma, pi, delta, and the sigma component is really missing here. This was incredibly exciting at the time because we were, for the first time, finding a new electronic configuration for a metal-metal multiple bond that had no analog in organic chemistry. Now, Malcolm was just, I can't tell you how exciting it was to sit in his office going over all this stuff. And then we had this surprise, and then I'll stop. And that was, if you studied the NMR carefully, we discovered actually that these two electronic configurations were in equilibrium with each other in hydrocarbon solution if you had the right conditions. Now, we always had big bulky ligands, and it was always axial-alkyl, but this is the case. And this molecule is sitting up, I spied it, it's sitting up there, the tetra carboxylate of bisbenzyl. So you have in this one, this is the ethyl group of the NMR. Sorry, the chemists will all recognize this. So you have one type of ethyl group, and that's the triplet and quartet there. And then when you had this equatorial alkyl, there were two types. And you can see they're marked in the asterisk up here. And you could change the solvent, you could get the equilibrium constants. This was quite surprising at the time. So I'm going to end with that and say that this is just a sort of short story of part of being in Malcolm's group. There were a lot of lessons that I learned that have always taken with me. The first was that the integration of synthesis, spectroscopy, and theory that I got out of this little story has stayed with me for my entire career. And that was a lesson that I got from Malcolm. It set the tone for me, and my story is not unique. There are many students here in the audience who've had similar stories that they can tell about their time with Malcolm and how his mentoring and his energy set the stage for their careers. So Malcolm had a very profound impact on everyone that he interacted with. I'm going to show a couple of pictures and then I'll stop. I promise I'll get off the stage. This is one of my favorite pictures. I don't know which of you two this is, okay? But you think it's you?
I know.
You think, okay. So Joey Money took this picture. Malcolm won the Guggenheim Award. This picture shows a lot of things. One is those stinky Russian cigars that he used to smoke. He's got one of those. And his mentoring ability. He's teaching one of these kids some very bad habits at a very early age. But he always did it with such care and such vigor. He was a lifelong friend. I mean, I didn't just graduate from IU and go off. for the next 30-some years, Malcolm was a friend and a colleague. This was a picture taken at an alumni event at IU 2 years ago. Malcolm, he wasn't feeling well, but he was having a great time. And we were joking around. I was lucky to have known Malcolm. He is not gone. To this day, when I write a paper, I ask myself, how would Malcolm say this? How would he approach this? It has had such an impact on me. He's not gone. So thank you for letting me come today. Working with Malcolm was one of the best things that ever happened to me. Thank you.